Okay, welcome back. Second video, chapter 15, pressure. Um, First of all, we talked earlier in the year that, um, atoms and molecules really behave more like waves than they do particles. And I talked about wave mechanics being calculus related and particle physics being more algebra related. But there are a couple of instances where we can use particle physics to make really good predictions about things. The phenomena of pressure and temperature are two of those things. And so it says, all right, pressure is created by the force and the number of the gas molecules colliding with a container wall. So your chapter really focuses on pressure when it comes to gases because they are so affected by things like temperature changes and the size of the container, and the actual number of particles, whereas with solids and liquids, it's a little bit different. So, what is the relationship between volume and pressure? Well, the smaller the container, the more collisions you get per second, and the greater the force. So, we would say that relationship is inversely proportional, right? We have a small volume, we have a large pressure. We have a large container, we have a smaller pressure. But I wanted to go back and review pressure in terms of solids and liquids a little bit from your middle school science if you didn't have it. First of all, on multiple choice questions, they may ask you about pressure. When it comes to solids and liquids, again, pressure is force divided by area. The only distinction I want to make here is that with a solid, we can grind it up into a powder, we can break it, we can cut it, we can change its shape. When we spread the mass of the substance out over the area, we reduce its force, its pressure. So in this example, they have a box, and if they lay it down on the long side, then it reduces the pressure here to 1,000 Pascal. We'll talk about the pressure units in a moment. And if you stand it on its end, then you have a much higher pressure. You are concentrating all of that force into a small area. The only difference with liquids are still about force spread out over area, but liquids have to do with the height of the liquid. For instance, like if you were to dive into the water, the force increases as you go further down. It has to do with the height of the water column, not necessarily so much with the mass of the material. So again, the example they're showing here, that you can have less liquid in each of these four containers, this Pascal vase demonstration, but yet they all create the same pressure because they all create the same height of the liquid. All right, with gases, however, there are dramatic changes depending upon whether we alter pressure alter the volume of the container and the temperature, and the number of particles. So the relationship that they're talking about here in chapter 15 is going to be mathematically studied in chapter 18 called Boyle's law, and it is a inverse proportion. In the first example to the left, if we have a 1 liter container, that particular gas produces what they call 1 atmosphere of pressure. Again, we'll get to the pressure units in just a moment. If you cut the size of the container in half, now the pressure doubles from half a liter to 2 atmospheres, and then it doubles again if you continue to cut that in half. So on the right-hand example, we've cut the container to 1/4, a quarter of a liter, and the pressure has risen from 1 atmosphere to 4 atmospheres. So again, an inverse algebraic proportion. But it's also, and I don't wait till chapter 18 to do this, it's also greatly affected by temperature. It's greatly affected by the number of gas particles itself. And these are all linear algebraic proportions, most of which are direct proportions. For instance, with Gay-Lussac's law, if you increase the temperature, you are directly changing the pressure. So the example that they're showing you is that container in the ice bath has 1 atmosphere, and then when you put it in a boiling water bath, it goes up 37%. And that's because the difference in absolute temperature between freezing and boiling is not 0 to 100, that would be infinity. It's actually measured in something called kelvins. And on the Kelvin scale, the smallest temperature would be 0. 0 Kelvin would be the temperature at which particles stop moving. And freezing water has a temperature of 273 Kelvin. Boiling has 373 Kelvin. And so 37% higher, the pressure goes up 37%. So it's a direct proportion. So what do they want you to know on this test? Glad you asked. First of all, sorry, this is my third attempt at this video, so I already have some notes and everything written out. When we're dealing with the abbreviations for these relationships, they're going to use capital P for pressure, capital T for temperature, and that temperature is going to be in what they call Kelvin scale, which means that it has a minimum of 0 Kelvin, no negative numbers. N for the number of moles of gas. I guess that's what the lowercase n is for. V, the reason why I show you the abbreviations is because of volume. When they talk about volume with gases, we said in the last video that if an oxygen molecule at normal room temperature and pressure was 6 feet tall, then the next nearest one would be 6 miles. That would be 6 miles away. That would be the scale of it. And so we don't really concern ourselves with the size of the actual particles, because think about it, if you doubled the size of the particle from 6 feet to 12 feet tall, then you would still be 6 miles away from the next nearest particle. The size of the particle really isn't going to make much of a difference. So when they talk about volume with gases, they're talking about the volume of the container it's in, not the volume of the actual particles. So they want you to know 4 things for this relationship. First, you have to be able to graph it in the first quadrant. So whenever they say pressure versus volume, or whatever versus whatever, A versus B, we put A on the y-axis, we put B on the x-axis, and if it's an inverse relationship, we just draw a straight line with a negative slope. Remember in the beginning of the year I said titles for graphs should be descriptive, but in this case we're just making a generalized graph of what happens to gases under normal conditions. So we can just title it P versus V, because we're not talking about a particular gas, we're not talking about a particular pressure or volume, we're just saying that this is a inverse relationship. It has a negative slope. Second thing they want you to know is the actual term. What does it mean? Inverse linear relationship. What that means, if you look at number 3, is that if one thing gets large, the other thing gets small. Like for instance, if we reduce the volume that I circled there in yellow, the pressure goes up. If we increase the volume, the pressure goes down. So most of the time in chemistry, we're not talking about independent and dependent variables, but the pressure is dependent on the actual volume. Fourth thing they want you to know is what they call an initial and final state equation. And in an initial final state equation, if you have an inverse relationship, we're going to use multiplication in the equation. If you have a direct linear relationship, we're going to use division or proportions for our equation. So in this one, if we say P1, V1, the 1 represents our initial conditions. P2, V2 would be any change that we would make. So let's say, for instance, we change the volume, then we could solve for P2 and predict the pressure. And again, we get really good predictions under most conditions for this. In chapter 19, we'll talk about the conditions where we don't, where you have to use calculus, but we, of course, at this level aren't going to do any calculus-like calculations. So rather than just the relationship between pressure and volume, I want you to know all 4 of them now, even though they show up in chapter 18. We'll do the actual calculations in chapter 18. So I could ask you about Gay-Lussac's law, which is the pressure versus temperature, the ice bath one that I showed you the little picture of. Again, first quadrant graph, P versus T, pressure is in the y-axis and temperature's on the x-axis, and this is a direct relationship. If we increase the temperature, that increases the pressure. Particles move around faster, they can collide more often with the container wall, and so we draw a positive slope. Now, why the first quadrant only? Well, again, we don't have negative pressures. Well, you say, well, you can have negative temperatures. No, you can have negative temperatures in the Celsius and Fahrenheit scale. But in science, we don't use Celsius or Fahrenheit to do our calculations. We use the Kelvin scale, which has a minimum value of 0, so everything's in the first quadrant. Again, the little arrows next to the P and T. If one goes up, the other goes up. If one goes down, the other goes down. And the term direct linear relationship is what we would call that. And we said for initial and final state equations, if you have a direct proportion, then we're going to use division. So P1 over T1, our initial pressure and temperature, would be equal to P2 over T2. Any changes we would make. Third relationship, Charles's law. These are all named after scientists, last names, by the way. Volume versus temperature. Again, volume on the Y, temperature on the X. As temperature goes up, we get expansion. As it goes down, we get contraction. So this is a direct relationship. As one goes up, the other goes up. As one goes down, the other goes down. So we have a positive slope. And with any direct linear relationship, we're going to use division. So V1 over T1 equals V2 over T2. And the last relationship is called Avogadro's law. Now, Avogadro is the 6.022 times 10 to the 23rd guy for the moles. He didn't actually come up with the number. It was named in honor of him because of his work with gases. And he proved that there was a direct linear relationship between the number of particles you have in a container and the pressure. If you double the amount of particles, you double the pressure. And again, that relationship, we're going to use division when we have a direct linear relationship. So P1 over M1 equals P2 over N2. All right. The actual pressure units. The SI unit for pressure is the Pascal. The standard atmospheric pressure, they use kilopascal. At least they're supposed to. All the textbooks that I have from the college level that I teach out of use what's called the atmosphere. Now, when they say standard atmospheric pressure, do understand that that pressure is based upon how much air you have above you. So if you are at a low elevation, like sea level, you're going to have a lot more air in the column above you than if you are at the top of a mountain like in Denver, Colorado. So when they say standard atmospheric pressure, we know that pressure changes depending upon weather systems, and it changes depending upon elevation. For instance, South Brunswick, you are 200 feet above sea level. So very rarely do you get a perfect 1.000 atmospheres of pressure. Instead, what it is, it's more like an average, and they say it's about the average atmospheric pressure at sea level when it's 0 degrees Celsius outside. Now, why they chose 0 degrees Celsius, I have no idea. As far as the Pascal unit itself, it's a Newton divided by meter squared, so force over area, right? That was the definition of pressure. And a Newton is a kilogram meter per second squared. And so if we took 2.2 pounds and spread it out over the surface of a meter squared, which is about 121 square feet, and then we accelerated that at the rate of a meter per second, that would be a Pascal. And I always say, well, does that make sense? And students smile and nod their heads politely. And I say, you're absolutely crazy. That makes no sense whatsoever. Remember when I said the candela was about the amount of brightness you get for burning a candle for a second, and the joule was about the amount of energy you get for burning a candle for a second? A Pascal would be about the amount of force pressure you have from holding a paper clip in your hand. And it's not a lot of force. In fact, air pressure, which you rarely notice unless it's windy, is 101,325 pascals. Now, the last unit I consider the most important, and this is this 760 millimeters of mercury unit. Now, why do they use that? Pressure can't be measured directly. Pressure gauges, what they do is they have mercury in them, liquid mercury, and they attach the gauge to the sample of gas, and then the gas pushes against the mercury. And if it moves at 760 millimeters, that's an indication that you have what's called 1 atmosphere of pressure, or 101.325 kilopascals. Now, on the test, they want you to do conversions with this. You do not have to memorize the values. The conversions will be given to you. But let's take a look at them to review our technique on conversions. First one, and I did these prior, so I kind of left some of it up here. 265 kilopascal, how many atmospheres is that? Well, we're going to use the same techniques we always have. Start with what they give you, 265 kilopascal, multiply by a fraction, get the unit to cancel out, and convert to your new base unit. Now, we look up the value. 1 atmosphere is 101.325 kilopascal, so we get 2.62 atmospheres. To convert from kilopascal to pascal, we still have people screwing this up. Guys, got to be careful with this. Remember, set up your fraction. Kilopascal cancels out. And we're going to convert to Pascal. The larger entity, you have less of the large entity, more of the small entity. So the large entity gets the value 1. And now the term kilo means 1,000, but we put the 1,000 next to the Pascal. There's 1,000 pascals and a kilopascal, and we get 4,780 Pascal. And then the last one, I want to convert millimeters of mercury to atmospheres. So again, start with what they give you, multiply by a fraction, get the units to cancel out, and now we can look up the value. 1 atmosphere is equal to 760 millimeters of mercury, so we get 0.304 atmospheres. Okay, actual pressure gauges, the calculations for them I'm going to do in the next video, so thank you very much.